which is this. This you divide L, right? Divide L into square. So that lambda value will allow solution for this problem. Yeah, so this lambda, we call it the eigenvalue. But we have multiple lambda values that will allow solution for that boundary value problem, non-trivial solutions of that boundary value problem. Okay, so let's label it with lambda sub n, because we have so many choices. Lambda sub n. So those are a sequence of eigenvalues. Yeah, lambda sub n. Then, okay, with that lambda n, you put here, you will solve for phi, right? We know with that lambda n, we will be able to solve. We will find non-trivial solution of this boundary value problem, right? So we can put this lambda n into that, then we will find the solution. You see, with that lambda n, what is the solution? Solution of this or this, right? We just discussed. That will give a non-trivial solution. This will give a non-trivial solution with one term. Yeah, so we can quickly give the non-trivial solution. So with this, the phi sub n will be this alpha. It's also up to a constant, right? So if you remove the constant, that's fine. We just know that corresponding eigenfunction. This is called eigenfunction, which is solution of the boundary value problem. Cosine square root of lambda, this. Yeah, that's. Okay, so now to summarize, we have non-trivial solution for this case. So we didn't put the arbitrary constant, but certainly it's a unique up to arbitrary constant, right? You can put alpha, any arbitrary alpha here, still a solution of that boundary value problem phi. Okay, so right now we can actually give all the solutions. So that's the one. And this is actually a special case. You see, when n is 0, the lambda is 0, right? When n is 0, that covered this case. Because this is lambda equals 0. Yeah, when n is 0, lambda is 0. So you can include 0, because if you include 0, that will be the previous case. This formula actually will include this case if I include 0 for n. Right? Try when n is 0, lambda is 0, that's the previous case. And then when n is 0, that's a cosine 0, which is 1, right? That's 1. So this is really, if we include 0, so we can also cover that previous case as well. So to summarize this, lambda n, we just use this. And the phi n will be n from 0, 1, 2. So yeah, we have a sequence. So including that, non-trivial. So we have so many non-trivial solutions. Okay, now we're done with this part. This one, quickly you can get h, because that's essentially the same problem, right? So the h is what? Same problem. You see, this is when lambda is 0, all the whole point when this coefficient is 0, all positive, right? Just those two cases. So then our solution will be constant or in this form. Yeah, similar form. So we can write h of t. Yeah, so the h of t is in that form. Yeah, we can call it alpha plus beta. Yeah, beta, no, there's no. So then this is h of t, and also this is the 1. And then a general, because we, yeah, phi n. So now now this Hn will be this form, right, without worrying about boundary condition. So this is only ODE, we will give this form only, general form. So this one will be this form, right, just general form. And that one is this form.
Is that H naught of T or H1 of T?
H, well, we choose the 0 as the index because we include that case.
Okay.
Yeah, so we can use a 0. Then from 1, 2, 3, we will have this form. Yeah. So what is this? With the extra c, square root of lambda c, right? So the c will be also part of this. H. So of course you can take a square root. It's c, so that's fine.
T.
Yeah. So beta sine square root of lambda c outside t. Yeah. So you see we have h. We have p, and then when you multiply, now we have for each lambda n, each possible lambda n, you will find a phi n, right? You will find an hn, and you multiply, you will get one solution. But you will find many solutions in this form because the corresponding phi n and hn, right? Phi n and hn corresponding to the same lambda will give a product solution. Yeah, will give a solution in this product form. And that's one solution. But we know this homogeneous equation because of the superposition principle. If you arbitrary linear combination of those will still be a solution. So we can give a series solution. So quickly we series solution is this, just an arbitrary constant in the front. And from 0 to infinity. Phi 0, h 0, from 0 this time, including that lambda being 0 in that case. So